Welcome back to this post-conference part of the meeting, what we used to call user meeting of CSCS, and then later the network meetings, the PASC network meetings. So my goal is this next hour, or maybe half hour and discussions, to give you an overview of the upcoming upgrade and how things are going to continue with PASC after 2016. And it turns out the timing of this conference for this talk is not extremely good, because we are before ISC and we are before the steering committee meeting. So PASC has a steering committee, and that is going to happen next week. So some of the things I'm saying, will need final confirmations. I have to wait until the presidents make their decisions, to be certain about everything. And the vendors like Intel, I see Claudio there, they are going to make lots of announcements at ISC, and I cannot preempt those. So I will be light on technical details, and I hope you understand that. And you are not pushing me to break any NDAs, because I will not, that for sure. Okay, so last year we had a lot going on since we met the last time. We had 2 reviews at CSCS, one of the entire center mid last year, and then the PASC review that several of you were. It's very hard to see you, because I have the light here. I have to get used to that. We had the PASC review that also went well and is basically the foundation for how things are going to continue. But probably the most important story had actually to do with this system of MeteoSwiss that was announced by HPC Wire and inside HPC as the first GPU-based system that would run operational weather forecasting. So it's a machine that is packed with GPUs and is meant to replace the current production system of MeteoSwiss. So for those of you who may not know, ETH since many decades has been running the operational weather forecasting for MeteoSwiss. So the systems, MeteoSwiss owns the model, but ETH has been running these simulations initially on the research systems, and then when some 10 or 12 years ago they started to use up a large fraction of the research systems, we went over to having a separate operational system at CSCS. And so this is Albis and Lema, the 2 machines. It's actually 2 machines in one here. One is the production system, and then another one is used for research and as a failover system if the production system goes down. And what they've been running on this until March of this year is the operational forecast that consists of taking in data from ECMWF. You've heard some of ECMWF mentioned in some of the talks during the conference. So they run the global model and do the mid-range weather forecasting. And MeteoSwiss is, of course, a member of ECMWF. And then they ran a model at 7-kilometer resolution. And this would provide the initial and the boundary conditions for a 2-kilometer resolution model over the Alpine region. And you need the high resolution because of the orography due to the Alps. And then from this they would generate the data and the information then that the TV, for example, and radio use for their forecasts, air traffic control uses, and the number of other services that they provide. And So this has been running for several years, and much of the weather forecast that you hear on TV is based on these simulations. And of course, these things have to develop. So MeteoSwiss has been working on a higher resolution model for quite a while. And this is now meant to give you an example why the resolutions are so important. So this is, I always get this mixed. This is the Roistal with the Urnersee. So in English, I think it's called Lake Lucerne, the Urner part of Vierwaldstätter See, which is called Lake Lucerne. And this is Leventina. And both are very important valleys in terms of these, what we call Föhn winds in German. So if you predict the winds right in these valleys, then you have a chance at predicting when the weather is going to turn from still being good to bad. And so the data they are showing here is the mean data, during a day. And so this is measured data, and this is the simulated data, or measured from the simulation in the 2-kilometer model that was running up until March. And this is just showing you the impact of this change in resolution, this additional kilometer. And I think Christoph Scher is in the room somewhere, and I think he also made in different work, he made clear that using, somewhere around a kilometer or half a kilometer resolution is where you have to go if you want to get, at least in a statistical sense, the convective clouds right over the Alpine region. So that was one improvement, and doubling the resolution means a factor 10 in performance. Another important thing is you can see from what I showed before, MeteoSwiss was running one trajectory. And since this is a chaotic systems and we have uncertainty in the initial conditions, you would have to run multiple trajectories and then try to make some statistical prediction about the future state. And I don't know why. Okay, so in copying over, I must have missed the distribution in the end. But there is, again, a reality to this. So this is showing from test runs that were going on last year. So this is showing actually the forecast that was running in the 2-kilometer model in July. Forecast of precipitation, and I'm sorry, Oli, if I'm presenting this in a bit too simple way. I should have you present this here. You should look at Adelboden, that here has actually relatively low precipitation in the forecast, and then you have the ensemble forecast at the same 2-kilometer, but where you run multiple members. And you see there were a few instances where you had much higher precipitation. And then you can do the statistical average, and you go up in the precipitation. Here you see, I think it's hard to see the mean, or for me to read. Then you have the 10, 90 percentile and mean max. And then the control, which I believe is what then really happened. Is that, Oli? Okay, okay. And what really happened was actually this, that they did have quite significant precipitation, that the original forecast missed, but the tests that were running, so actually the ensemble forecast was running last year, but it was not validated yet, so they couldn't use it for the real forecast. And so due to now this new model and the new system, they've been running the 1-kilometer model, so single trajectory for model trajectory for 1 kilometer, and the ensemble. So this started in April, and this started in May of this year. Now, from an HPC point of view, what I want to point out is that the change in simulation performance. So going from the 2 kilometer model to the 1 kilometer model, I said before, is about the factor 10 in simulation performance. Then doing this ensemble simulation at 2 kilometer, 20 members, and then a little bit longer forecast, this amounts to a factor 26. And because of this higher resolution in ensemble, they also had to improve their data assimilation, and they pick up another factor 5 compared to the model that was running until on the older machine. So if you do this together, we have a factor 40 over the previous machine. So increase in simulation performance. We don't care about flops or gigabytes per second, but in the performance of the simulation by a factor 40. And this is compared to a machine that we had procured in 2012. And we had to put the new machine in place in 2015, so 3 years later. And so just to tell you, the problem we were facing at CSCS, because we have the mandate to support MeteoSwiss, you can say, okay, the machine, Albis and Lemma is this machine. This is the machine room of CSCS. And if you, we procured this system in spring 2012, and we had to put the new system in place sometime around summer last year, and to get it operational then by the fall. So as I said, in these 3 years, we could probably, if we make a conservative estimate, assume the processor performance goes up a factor 2. Okay, so that means if we now, so you take a factor 40, that's you need a factor of 20 more somehow in sockets, and you have somewhere around 300 sockets in here, so then, and you double the density in the Cray XE, so in the end you need 30 Cray XE cabinets. And this is Piz Daint and Piz Dora, so this is the area of 40 cabinets. You see a few slots are empty here, but that's roughly the area we would need. So if we were just to take the code and buy a bigger machine, of roughly the same architecture, then we would need an area like this. And the price is roughly proportional to the area, and also the power consumption is roughly proportional to the area. So you can see here visually how much the procurement price would have gone up and how much the power consumption would have gone up. Now, MeteoSwiss was at the time paying for the power, so that would have been their problem. But I had the mandate to help them with the investments, and this would have been my problem, and basically eating away at anything we do in the future on Piz Daint. So obviously this was not an option, and we had to take a different route. And the route we took, and this is now very important because it is an outcome of the HP2C program, the precursor to PASC, and then also PASC. So we started with investing in software refactoring as part of an HP2. So it was one of the several HP2C projects that we started in the fall of 2010. And there was one project that was refactoring the dynamical core. That was roughly in about 1.5 years. We refactored the dynamics of the Cosmo model. And we being C2SM, the climate center at ETH in collaboration, and MeteoSwiss is a member of that. And then there was a second project that was really, when we saw this would actually work with refactoring, then really invested, and there also MeteoSwiss invested in really getting a production code to run. The motivation at the time was actually to get this code to run productively on Piz Daint. And so there were a number of codes, 9 that we were looking at from the HP2C program, and we were evaluating different architectures in 2011 and 2012 that then in the end led to the decision to build Piz Daint with GPUs. And so we could build on this important outcome from the HP2C program that later became PASC. And we could build on that to deal with this factor 40. And so this was then a 2-year co-design effort of now not a general purpose machine, but really an appliance for weather forecasting. And I can go on and on about co-design, that it is important that you build horizontal solution first, and then later on, from that technology, build vertical solutions, and how to do this right. And we then ended up being on time and on scope and within the budget envelope that we had. And then even MeteoSwiss, with their part, ended up being on time, so they could start running the model this spring. So what I would like to do, give you some numbers, because what we now have is, we have the current code that was running up to now, that is running on both, hardware of the time, 2012, actually would even run on vector machines, and is running on the newer Xeon processors. Then we have the new code that is running on Xeon processor, the hardware of the time, and the new hardware, and is running on GPUs, and eventually also will run on Xeon Phis. And so now I can compare machines to each other and different codes, and I can ask questions. How much did we gain by just replacing the processors from older to newer processors, or how much did we gain by refactoring the software in various parts? How much do we gain from architecture, and so on? So what you can say is just the processor performance. So take the old code and move it from the past machine of 2012 to a newer Haswell processor in 2015, and that would have given you roughly a factor 3. So 2 was a bit conservative. It was a bit more. It was 2.8. What we call here improved system utilization, actually, it may be a bit too simplistic here, so I have to explain there. The MeteoSwiss changed the algorithms to go from simply strict double precision to a large part of the model running in single precision, some still running in double precision. So it's, strictly speaking, it's mixed precision, but mostly single precision. And I think we've heard one of the talks, and probably several talks in some of the climate sessions about this issue of precisions or lowering precision. So much of this 2.8 is coming from this, but then also, since we have now full control over the code, we could also reduce the margin we have on the machine and actually fill it up more. So it's a combination of the two. Then, and this is software improvement. So this is running the old and the new code and comparing them against each other, almost a factor 2. And so, and this is a professionally written code that we started with that, was already doing well on performance, but even that you can refactor and still double the performance. And then you have the moving to the new architecture, so the GPUs. So now you can make a comparison. This is what Moore's law gave you in 3 years. And this is what software refactoring gave you, namely speeding up the code and being able to now choose a better architecture. So that's almost a factor 4, and this is not quite a factor, or no, this is a factor 4, and this is not quite a factor 3. So I think this is very good motivation for why one should invest in software. And you can now do the numbers, how long this has to run the new system to amortize the investments in software. In fact, it doesn't have to run long, because just the investment cost is already by factors, giving us the return we need to pay for the software investments. And then in order to get to the factor 40, we need 30% more sockets, and that gives you the factor 40. And on top of all, because the GPUs run very efficiently when they run in a bandwidth limited mode, so we gain a lot on the power or the energy consumption as well. And the result is then a machine that doesn't have this huge footprint, so the machine room still has space for large future systems, but has a comparable footprint, and actually the energy footprint was reduced by about 30%. And the difference in cost we can now invest in maintenance of this software. And so the consequences for PASC are actually quite significant. So ETH Zurich has this mandate, and this was renewed to help MeteoSwiss developing the next generation model, which is going to be deployed in 2023. So this is going to keep us busy and keep ETH investing in scientific computing and keep the federal government to invest in scientific computing. And I believe this is good for the whole community to have something like this, like an anchor that will keep us and PASC and HPCN going at least for another 2 budget cycles. And the other, we would say almost historic thing that happened on May 4th is that the Federal Council then made a decision to fund future systems of MeteoSwiss out of the federal budget, so it's not charged against anything in the ETH domain anymore. And I think this was, again, in recognition of the work that they have done in these HB2C and PASC projects. And so I think this is good news for PASC, and because, I've shown this time evolution before with the systems that we built, the investments we made in software, and how they have influenced the hardware design, like Piz Daint that I mentioned before, and then the PASC program that we are talking about here, and I will move forward. The evolution of the hardware that is driven by this investment in software. And I had talked during the review last December that we had put in a proposal both to continue HPCN, so the investment in systems, but also to continue the investment in PASC. And so this is the difference compared to last December, is that this, from a budget point of view, has been confirmed. So we are really going to continue the program approximately at the same level. I will come back to this, of investments in the future. And but we will spend more money generally on software and application development in the future, and also the investments in a system that will eventually replace Piz Daint, that we expect will be installed in the time frame 1920. Is also now in the planning for the budgets. And I will come back to this point, that we really see the role of PASC will be similar to the role of HPCN in the past, to really motivate and get the software ready for the systems that develop at CSCS. Now, very briefly, or I will say a few words about the upgrade. And again, I want to put this in the context of, because the upgrade of Piz Daint is not a new system. It's really completing something that we have been working since the 2009 timeframe. Remember, 2009 is when the initiative, HPCN initiative, was approved by Parliament, and then these initial investments started in Monte Rosa and in the HB2C program, and then the construction of the new data center. This was believed to be a successful combination. which is the combination of a new and flexible building infrastructure, efficient supercomputers, and efficient applications. And so then the university conference decided to fund PASC as a continuation of HP2C. And the original plan of HPCN was to fund something like Piz Daint, namely a petascale supercomputer. And so we had the first phase of Piz Daint. It was installed in late 2012, and it picked up operation in the user program in spring 2013, and was then running through the end of 13, and then we had an upgrade and an extension, which is Piz Daint as you know it today. And so it was always planned that after 3 years we would have basically a refresh of the nodes. And so this is the second phase. So I started, okay, sorry, it's the third phase. I have to correct this. Phase 1 was here, phase 2, and then the upgrade is really completing Piz Daint. And then it will reach end of life, we expect around 2020. And so, you know, there was many discussions about whether this investment in GPUs was, you know, short-sighted or, you know, is the trend. And I think now what I'm trying to do and convince you that we are, you know, not outliers, but we are in a trend that is going on. And what I'm looking here is at the machines, some of the leading systems around the world. So this is Tsubame at Tokyo Institute of Technology, is a GPU accelerated system. This is K-Computer, which I believe was in 2011 became the leading machine on the top 500 list. A distributed multi-core system. Then we had Titan in 2012, and we had Mira in also around the same time in 2012. And then Tianhe 2 came in 13. Okay, yeah, spring of 13, exactly, ISC of 13. And Piz Daint started in 12, but then was extended and upgraded. And at the same time, we had Edison, which actually should be over here. But I'm going to show you, because NERSC is on a slightly different trajectory now. We have because these are two DARPA HPCS systems. And so the trajectory here is that one of these is the line of GPU accelerated systems, and then the other line with Cori, that is the successor of Edison, also a KXE system that is on the Xeon Phi accelerated line. And we have new Japanese systems coming up, so Piz Daint will be here upgraded, and then we have Tsubame 3, and we have a system at University of Tokyo and Tsukuba that will be there, and then Summit, of course, that many of you know about, and Aurora. These are then the two big DOE systems that are coming in the time frame beyond 2017, 18, 19 time frame. And we do have POST-K, which I believe is on this track here. And but you see that the main investments really at the high end, and this is where things will develop eventually into exascale, are happening in these two areas. And this I showed in the climate session yesterday. I just keep repeating. All the big weather systems are in this path, except for the MeteoSwiss system that is over here. I told you what the motivation was and why we did it this way. And of course, you can, if you're sitting at Deutscher Wetterdienst and you say this is an outlier. But I believe if you're saying, if you look at how systems are going to develop in the future, I think everybody will have to look at these developments over here, Xeon Phi and GPUs, and do the necessary software investments to be able to follow these paths. And the main point, I do understand that they are quite profoundly different architectures, but there is something that they have in common, and they have heterogeneous memory. And the way this manifests itself on the GPU accelerated systems today is we have this graphics memory along the GPUs, and we have then the DRAM. And when you try to abstract this, you have a network. You have low latency threads. You have many throughput threads on the GPUs, and we have these two types of memory. And when you look at the Xeon Phi processor, this one I'm authorized of showing, then you will again find that you have the high bandwidth memory on package, and you have the DDR memory, and so you do have this heterogeneity. And we heard from Mark Sneer on the first day, the opening talk of the conference, that this being able to deal with these different types of memory is going to be important, even though they will become eventually, you will have the option to run things in a coherent way. So you can have the system manage the memory for you, or you can, in an HPC sense, when you care about performance, really worry about this heterogeneity. And this is something that we have to, I believe, we have to worry about when we talk about algorithms. So one announcement I can make is that we will, at CSCS, have a development system. So this will be a Cray system, so an XC. I don't know what the name will be. Cray will announce that either I don't know, at ISC or maybe in the fall. They will have a product name behind this. But it's, again, based on the Aries network and the XC packaging. So similar to what we have in Daint. And so it's actually part of the Daint upgrade will be this will be a Xeon Phi system that we will run as a development system, and I think this is going to be one of the important systems for PASC to move forward. And I will come to this again. I will stress this multiple times, that PASC, as we move forward, really has to look at these emerging architectures. In the case of the hybrid part, or what will remain the hybrid part, so it will be a fewer cabinets, we will basically replace the Xeon processor from Sandy Bridge, upgrade to Haswell. I will explain why. This will come along with an upgrade of the memory from DDR3 to DDR4, and we will have 64 gigabytes per node. And then we will upgrade the GPU from Kepler to Pascal with 16 gigabytes of on-package high bandwidth memory, so similar to the Xeon Phi you saw before. And the reason actually why we upgrade both here, or one of the reasons, not just to get performance and higher bandwidth and so on, is then we can run the connection here, which currently runs on Gen 2, PCIe Gen 2, will pretty much double the bandwidth. And then when you consider that we have then here the same bandwidth as between the Xeon and the NIC. So this is the Aries system on a chip with the NICs and the routers here. We will have pretty much the bottleneck for large scalable computations will no longer be here, but it will be in the injection bandwidth into the fabric. And I believe that's around 9 gigabytes per second. So both here and here we will be above that. And then the injection bandwidth and the bisection per node are about comparable on this system. So it's not just the performance of the node, but also we believe the network performance when we have distributed memory over the GPU memory and using GPU direct across the system that will improve. And so if I now go back to this, the various systems that are out there and the three types of systems that we will have, well, Piz Daint will have a hybrid part and it will have a multi-core part. So the one thing I haven't said is that we will merge, merge the two. So what is called Piz Dora today and Piz Daint will merge into one system. So they will both be, you will still have multi-core only nodes and hybrid nodes, and they will be in one fabric. But then we will also have this development system with Xeon Phi. So from a point of view of PASC and development of future applications, we will really be covered with all the architectures at a fairly large scale, and we will have test systems and development systems for other architectures. Like we will be exploring ARM, we will also be exploring Power and also NVLink and these things. So you will really have the ability to look at everything that is coming. And so this is there is going to be an expectation that future PASC projects really pay attention to this, probably even more so than in the past. So about what can we expect in PASC? So I think the most important thing that you need to get prepared, in your thoughts, also those of you who have PASC projects or those of you who are interested in going in this direction in the future, is that we will in the late summer, so end of August, early September, we will have a call. I have here an asterisk because this is what I'm proposing to the steering committee, and I'm expecting them to approve it, but formally this is not my decision, it's the decision of the steering committee. When you look again at this development and the things we've done in the past, namely use these programs to influence the systems, we are really expecting the programs that we will invest here to really drive or help drive the decisions we are going to make about architectures at the end of the decade when we build the replacement for Piz Daint. So this will be one thing that will be showing the call, that we will really have a strong emphasis on novel architectures for future HPCN systems at CSCS. And so, really think about using Xeon Phi in applications, GPUs, ARM, and this I mean here just to say for heterogeneous memory, so high bandwidth memory, SSDs, and so on. Those will be important topics to look at. And the second thing that will be different in the future is that the funding for PASC will come, is basically ETH domain funding that goes to ETH. So it is funding that ETH Zurich is accountable for. In the past, most of PASC was funded through the university conference and was earmarked for universities. And so that earmark will no longer be there, but ETH is going to open, so the call will be open to all academic institutions. So we are not looking, so it's really a national program. It's not an ETH only program. But again, the ETH is responsible or will be held accountable for what is happening in details. So that's pretty much what I have to say. I think the most important news is that there will be a refresh in the architectures at the end of the year, and that we believe we will be covering the whole spectrum of what is available in the coming years, and we will continue to make sure that we make the whole spectrum available And we are also expecting then that the application developers in Switzerland pick up this opportunity and really invest in software development, and we will help this software development with the PASC program. And I think the best news for also this conference is that these investments will continue. Switzerland, for those of you who are not so experienced with Switzerland, we are on a 4-year cycle with our budget planning, and the next cycle is from 17 to 20. So when we talk about we end here at 20, it doesn't mean that things will stop. As I said, the MeteoSwiss mandate will continue into the next decade. So I expect that HPC and scientific computing will be healthy and continue to prosper even in the next decade, and then in the next cycle, which will be 21 to 24. And so I very much look forward to working with you at all levels, whether it's systems or applications, and I think the work can continue. Thank you. So, yes, we can have discussions. Okay, and now I see everybody. It's very strange when you have light in your face, but you don't see the people. Are there questions? Simone? I think they want the microphone.
Thank you. So to look just 1 year ahead before going to 4 years, the current PASC fundings are usable until end of the year, or did you?
If I remember Benedetto, so this is Benedetto Lepore at USI, they are managing the whole thing. Then certainly the funding will go until spring 2017, and I think has to be spent by then. Benedetto, I know, is not here, but maybe yes,
2017.
Yes, June 17.
Projects, yes.
Okay.
The funds, I'm not 100%.
Okay, and the plan with creating the call in the fall or late summer is then there will be there is going to be a deadline for the proposals around, I believe, in October. The numbers I will have to the dates, and then there will be a period for the review and the decision at the end of the year, and the new funding will then pick up in the spring or so of 2017. So in principle, PASC really continues without a gap. So we're trying to arrange it that way. The steering committee has to approve it. This is, I believe, Pedro. Okay.
So probably a more abstract question. You're provisioning for multi-cores, for GPUs, and for PHYs, which are systems that we know exist. What do you have, like a room in the budget or like in the planning somewhere for things that we don't know that are going to happen yet?
Yes, of course. So we have always at CSCS, we will always have systems, development systems or test systems. With, as I said, ARM is something we are looking at, and the power, open power systems. So we have that. We've done that in the past, and we are doing it in the future. I think what we do, maybe similarly to some of the leadership facilities in the US, although we are not trying to be in that scale of the size of the systems, but we are deploying, the novel architectures at scale as well. So we really encourage, we try to support the the development of future applications and libraries and algorithms with test systems, but we try to give as early as possible. We try to give access, to systems at scale. We are also working, of course, closely with partners in Europe and the US, but we want to have some of these systems ourselves because that allows you. There's not just the application part, there is other parts of the software stack that we need to help develop and influence. So it's both things that we are doing.
I just wanted to know if you could explain a little bit the thinking behind merging of Dora and Piz Daint, the two different hardwares, and having them on the same network, what the thought behind that was.
Okay, good question. So what we would like to do is eventually, first I believe this is a trend that we will see in other places, and we are not, there's one other place that's doing the same thing, and that's NERSC with Cori. Okay, there may be other centers I don't know of, but we've been talking or collaborating with NERSC, of course, and so they have, I think, a Haswell partition, and then they are building the second phase. So that was the first phase of Cori, and then the second phase of Cori with Xeon Phi. And ours is similar. We have a Broadwell partition that you know of because we just upgraded Dora, and then we have the hybrid partition. And the reason from a technical point of view, there are multiple reasons. So you would like to have, we would like to support as much as possible a workflow end-to-end on one system. So eventually, you can imagine that you keep things in memory and you just move things around on a machine using the high bandwidth that you have on the network, so that you can do complex workflows without having to go through I/O. So we would like to encourage, and this is something that some of you certainly have seen in the past, encourage the thinking of in situ data analysis. We had this work with the Peter Messmer, I don't know if he's here, has been doing with the Bonsai code, I believe 2 years ago, where we did rendering and visualization of an astrophysics, so a galaxy simulation, while the simulation was running, and we were streaming the frames, to Louisiana at the time to SE as a demonstration. But the idea is, and we are pushing this also. There will be lots of discussion later in the climate network session. We are trying to push that this thing that you can do analysis while the simulation is running. And so that is one area. Another thing that we have on Piz Dora actually today are these burst buffers, or the SSDs. So these are I/O nodes that are integrated into the machine and have solid state disks on them. And were designed as real burst buffers, to take the short-term load and then stream out the data to the normal file system afterwards. Later, while the application goes on, so for checkpointing. But we are also exploring other ways to using this basically persistent memory that you have, or like persistent storage, again to support different workflows. And that is maybe in summary, some of the thinking behind. And you could even imagine that you have applications that use both, multi-core and hybrid accelerated things, nodes at the same time. Does that give you a satisfactory answer? Joost, I think.
So I have one question towards the system software stack. I mean, if we have now 3 architectures coming, so GPUs, Phi and multi-core, how are the vendor libraries going to deal with that? I mean, debugging, compilers, profiling, will this be in good shape?
Okay. Yes, so the 3 systems are from the same, or well, they are not 3 systems. They are essentially it's the same systems. You know, we are not changing
3 node types.
the 3 node types. They are basically the same overall architecture. So the software stack, the version of Linux and
I think
generally the software is the same on all of them. And now there are actually a number of features that that maybe Nick can talk to, but what you're basically, there is a second part to your question, whether the vendors can keep up maintaining efficient libraries for all these architectures. And I would defer there to Kay. You can ask them whether they can. I think this is something we need to think about deeply, and we are also looking at this from the point of view of PASC. So we're really considering actually investing some of or we will look at investing some of the software development. So the amount of money that will go into the calls will stay the same, and we will invest what we would have previously invested in hardware to support some of the library development, because I believe this is one of the crises that we have in supercomputing, that for distributed like Scale-Pack, you know, the current model is not working, okay? And this somehow we have to change. And so I will be talking to some of you, particularly about LAPACK. The material scientists in here know that I've asked about what electronic structure codes are using in Scale-Pack, and trying to get an understanding of where we should put the focus. And I think your answer, Joost, didn't help much, because you said you need everything. And that's, of course, not, you know, we have to somehow try to prioritize, but we are going to pay a lot of attention to this library issue. And not just we here. I know Department of Energy is going to make massive investments in the time frame of their exascale computing project in the next 5-6 years. But it's an important point, yeah.
Yes, I would like to continue and to ask on workflows actually, which are related to the question before that. So I'm a developer for both large-scale simulations and in situ visualization techniques. And I mean, one problem that we have with in situ visualization techniques is that we have to know where we want to look. So one question would be, if I would write the proposal for the next machine and I would like to do exactly the same simulation 10 times, would I get an approval for that? Because maybe at first and the third time I know where to look for. And the second question would be, usually after queuing for a long time, let's say a week, my simulation starts up at 4 a.m. where I am asleep. Would it be possible to, for example, or do you think about changing batch systems that, for example, I can use and re-RAM for some time until I'm awake?
Okay, so when I say, you know, we went into, we are going to look at this with workflows, and we are putting the system together. What I didn't mean that we will know how to do in situ visualization next year or next call. Okay, this will take some time, but there is a commitment on our part to really look at this with communities, and whether you know, you have to understand the way proposals are allocated. Okay, you ask for a resource. The resource actually mean real money. Okay, when you get you know, when you get millions of node hours allocations, that means millions of Swiss francs that you get allocated. And so for those who keep complaining that these reviews are pain in the neck, and so when you go and ask SNF for million Swiss francs per year allocations, they will also review what you're doing. And so the allocations will continue to be, who gets the allocations is based on the science case you're doing at that scale. But we envision, so whether an individual PI or a group will get it really depends on the science problem. But long term, I think one model that we should really think about, and this is one thing we're discussing in the climate network after this session, is think about the trajectories you saw for the weather. You can imagine those now being 10 times longer or 100 times longer for a climate simulation. Okay, and so today you would write climate. You would write some sort of correlation functions. You would somehow reduce the size of the data and write it out to disk at a certain time step, okay? And then afterwards you would analyze this data. And you could imagine now that you run a trajectory in a very lean way initially, and you checkpoint. And that turns out to be much less I/O that you then do. And then from the checkpoints, you rerun the simulation in parallel. And if you do it very well, you could do it, you run it, say, on some type of architecture, the lean calculation, and then you rerun it, say, on GPUs more in a throughput manner in parallel, provided you can reconstruct the trajectories, and you do the analysis. And the dream would be that similar to a large experimental facility, that you say, now we are going to run, next week we will run this and this model. Now, I have to say this is not next year, okay? This is a far out dream, that you run this and this model next week, every night, and then people can submit their scripts and analysis scripts, and then somehow they go through some validation process to make sure they don't destroy the simulation or block the simulation. And so you could imagine in that way to having, so you can go to sleep, and then at 9 when you wake up, you can look at the results and see if you have to go have another run. That is one potential model that we are thinking. But there are many other things that could go on. There is going to be, there are a lot of developments around data science, and so there are other use of large-scale systems that we are trying to get ready. And also NERSC, I know, and Craig is also developing things in that direction.
Okay, I think we have to thank you, Thomas, for this talk.
Okay, time's up, yeah.
You still have questions, I mean, Thomas.
Yeah, I'm around, yeah.
But Michele wants to say something.
Yes, this morning we found a camera in the back. If you are missing a camera, then it's just a registration desk. And if you hear from someone that lost his camera, we will leave it here at the center so that they can ask here. And if there are additional questions respect to CSCS, Maria Grazia, Nick, and me, and other people of CSCS will stay a little bit longer in the room, so you can contact us directly if you are not to go to one of these network discussions. Thank you very much.
Yeah. So I recommend you talk to Nick. There are some specifics also about the system after the upgrade will change in a number of ways, interesting ways, and so please take advantage of that. Yeah, thank you.